Hi, good morning, students. In a previous clip, we have discussed about example 7 to 17. Right now, we will discuss about the example 2.18. Actually, in Gujarati medium book, there is no availability of this example, but in English medium, it is available. So, we will solve it out. It is a good question as far our knowledge of parallax method is concerned. As our question or term suggests us that explain this common observation clearly. If you look out at the window of a fast moving train, nearby trees, houses, etc. seem to move rapidly in the direction opposite to the train's motion. It is called as the Newton's third law, or you can say that the relative velocity basically. So you can see that, but the distant object with the hilltops, moon, stars, etc. seem to be stationary. So right now we are not applying any type of force. So proper word is not Newton's third law. Proper word is that it is called as a relative velocity or relative motion. But yes, if our amount of force applied by our train on the air, then we can apply Newton's third law as per short. So we have to just see that why this such type of thing is possible. So first of all, it is called as our eyes point towards the position is called as a line of sight. And you will know that I have discussed in the parallax method. Let's say I have these points A and B. If my theta is larger, it will look like that my object is far away, then theta is smaller, and object is very much nearer to me, then theta is comparatively larger. So these are the things we can say that. Where you can say that houses or relative cars having theta which is very much larger, that is why they can just seen very nearly and moving very fast. It is called as with the relative velocity of these objects are very much fast, while compared to that mountains. Okay, so for the angles, theta is larger or smaller. So let's say these are theta is larger, it is for the mountains and all those things which are very much larger to you or smaller to you. So you can say that theta is smaller only because of for the mountains, and theta is larger for the near objects. So these objects which are having theta very much less than, they will look like stationary, and that is the reason where in parallax method we have discussed that if my object is farther away or very much nearer, it is farther away and near, that is why I can see that if it is very much near, then theta is very much larger. So my theta's value is larger, object is very much near to me, I can easily count it out its velocity, which is moving very rapidly. But mountains or the distance or sometimes it is look like horizon is moving very easily or slowly, smoothly, or sometimes it will look like stationary. It is not actually stationary. So theta is very much lower. That is why these mountains and all those objects which are very much far away to us will look like very much stationary. So these are the reasons why we can say that my object is a farther or nearer. With the help of parallax method, you can answer such type of good questions. Now my question of example number 2.19 is like that. The principal parallax section in the 2.3.1, it is called as our theoretical portion, used in the determination of the distances of a very distant stars. Yes, it is useful for to find it out distances of stars or asteroids which are very much far from the surface of the earth. The baseline AB is a line joining the earth and the two local stars. So first of all, for my conveniency, I am doing a simple figure task. I am drawing a simple figure so I can have this thing. So first of all, I am drawing a figure, and I am drawing one baseline which is, as they have suggested, it is called as a AB, and this is my 2 points. I am just assuming that this is the distance of S dash or star or some object, and I am just joining these lines as per my convenience. You are aware about such type of angles, so I'm just putting two angles, theta and theta. So whole angle will be 2 theta. and this is my baseline. I am just naming it as a small b. So now you can just count it out, that is it is look like our simple notation which we were saying that it is called as our parallax method. And now our baseline is about the diameter of Earth's orbit is a 3 cross 10 to the power 11 meters. So first of all I am just saying that baseline's distance is called as a AB, and that is a 3 cross 10 to the power 11 meters. Now what I want to just suggest is that and now I want to utilize my notation which is called as a 3 cross 10 to the power 11 meters, and my angle is given to me, it is called as a parallax method of a 1 second. You are aware that in the normally when it is called as a 1 second, I want to convert in the terms of a radian. So directly what I am doing is that multiplying this my 1 second with multiply by 4.85 cross 10 to the power minus 6 radians. So this is my angle. So I got this my angle. I want to find it out some more data. So I am just using my parallax method. As per my parallax method, angle equals to arc upon radius. So I can just say that 2 theta is equals to b by l. This is my b and this is my distance l. So I can say that l equals to b divided by 2 theta. It is called as ab divided by 2 theta. So I can have 3 cross 10 to the power 11 meters, and this is 2, and my theta which is 1 multiplied by, that is why I am directly mentioning 485 10 to the power minus 6 radians. This is meter. So my length would be 10 to the power minus 6 is going in the numerator. It will give me the power 10 to the power plus 6, then that would be power 17. So I can, by calculation, I have already calculated 10 to the power 16 meters. But you are aware that it is look like 1 parsec. So I can also mention that 1 parsec equals to 3.08 cross 10 to the power 16 meters. So rather than writing meters, you can say that L equals to 1 parsec. So this is how you can calculate the distances or angle with parallax method, distance between the any planet. Now another co-join example. Why I am using this word co-join example? Because they have already asked almost the same data. You have to use previous data as well. The nearest star to our solar system is a 4.29 light years away. You are aware that light year is actually a distance. It is not the timing. So I am just using that distance is equals to 4.29. It is a light year. So I am mentioning that 4.29 multiply by, you have a 9.46 cross 10 to the power 15 meters, and you are very much aware that 1 light year is equals to 9.46 10 to the power 15 meters. So I got my distance is this much meters. So I'm just mentioning as a d. Now I want to find it out with the parallax method. With the parallax method, this star, one name is a star is called as Alpha Centauri. Show that it is viewed from the two location of the Earth. So I'm using that previous data. So I can have my 4.29 10 to the power 15 multiply by 9.46 divide by 3.08 10 to the power 16. So 10 to the power 15 and 10 to the power minus 16 minus 1. So I can get 1.318 parsec. So these are the data which are available to you. So you can also use over here parsec. So this is the data of a meter, and this is also data of a meter, or you can just say that parsec. So your unit would be meter per parsec. You can also mention that 1 parsec. So these are the data. From that you can say that It is following our simple and sober formula of parallax method. Now example number 2.21. In the measurement of a physical quantity in physics, you are in a need of so many primitive data, and that primitive data and same is the concept utilized when there was a world war. To think of different examples, and you have to give that appropriate example for that. It means that they want that why there is a need of accuracy in physics. Actually there are tremendous numerous examples of precision in physics. Let's say I am talking about let's say accuracy in the mass. So there are 10 to the power minus 34 kilogram to 10 to the power plus 35 kilograms. Such a difference of masses, approximately 10 to the power 69, is the difference between 10 to the power minus 34 to 10 to the power 35. Such type of accuracy would be needed. If you are talking about your distances, so you are aware about 1 femtometer, or for me there are some minus 15 meters. There sometimes we are in need of a 1 angstrom. Why we are using such type of a smaller units? Because of only one thing we are in a search of, that is called as accuracy. And if we are not keeping any accuracy in the measurement of mass or length, or sometimes in the terms of a time, that is called as a 10 to the power minus 9 seconds or nanoseconds, these are the very much smaller quantities. So in physics we are not compromising any point or any object whenever we are dealing with the accuracy part. That is why there are certain examples they want that we, if they are not certain about the speed aircraft or position of any location, then you cannot throw or you cannot have any point where you can deal with your actual demanded result. And that is the thing people had counted out in World War II. They have bombarded hydrogen bomb or nuclear weapons they have now created only because of such type of accuracy. So there are plenty of examples you can utilize, but right now we are having such type of data available to us. So as per your understanding, you can put any type of data. What they want here is that your knowledge or the gradual knowledge of some of this smaller and higher data which you have right now, utilize gradually. Now those data which I am talking about will now properly use over here, because in this example they want each and every question which are called as very rudimentary type of question or ideas. These are called as a very, you can say, sometimes you are itching your head because of such type of questions, and you are not in position to say that its answer would be this much accurately. Such type of questions are there, but right now we will use such type of question. We will use our knowledge and find it out its answers as well. So first of all, we are finding it out. Very first question is that, let's say I have in front of us is that total mass of a rain bearing cloud. Now it is called as a question. Good question. Likewise, in the previous question I have just asked you that what type of data you can collect, smaller and larger. Now this is the thing which you can utilize and find it out proper answers. They are called as your grasping type of question. In a total mass of a rain bearing cloud over the India during the monsoon, such is the question. So first of all, what I am doing is that I am just using that height from which my cloud is passing. I am using this data that is called as a 10 centimeter, and using that height of cloud or thickness of cloud, it is called as a 0.1 meters. Area of the cloud, I am assuming that it is in around, let's say I'm talking about India. The area of the cloud around India, the area of India is a 3.3 million kilometers. So I'm using that area is a 3.3 cross 10 to the power 6, and that is called as a kilometer. So I'm just converting in the terms of a meters. So 3.3 cross 10 to the power 6 cross 10 to the power 3 meters square. So you can have area of India, or area of a cloud around or above India, is 3.3 cross 10 to the power 12 meters square. Now I am just utilizing this data with the help of density of water. So you are aware about one formula of a volume equals to area multiplied by height. My area is a 3.3 cross 10 to the power 12 multiplied by height is let's say 0.1 meter. So my volume of India would be 3.3 cross 10 to the power 11 meter cube, because the area is called as a meter square and this is called as a meter. So this is the area of our India. And now I am using this with the help of a density of a water. So I'm using this notation. Density of water is equals to 10 to the power 3 kilogram per meter cube. You have to remember this data. Now I am utilizing all this data and now putting one formula. You are aware about density is equals to mass divided by volume. I want my mass, so I can have a mass equals to density multiplied by volume. So I have utilized all those data. Density of water is a rho W multiplied by volume is a V. So M is equals to 3.3 cross 10 to the power 11 is my volume and 10 to the power 3. So this is the actual mass of one cloud which is containing water. So this is how you can just utilize your data. So this is my mass. So with the help of a very simple mathematical calculation of some area and a volume, you can be in a position to find it out what would be the mass of our cloud. Now what I want to find it out is the second question, mass of elephant. This is the second question. B is called as the mass of an elephant. So with the help of one notation I am using and finding it out, mass of an elephant. So first of all I am utilizing question number second. So for the question number second I am putting that B, I want to find it out mass of elephant. For the mass of elephant I want to find it out. What I will do is that there are different type of logic people will apply. What logic I am using is that is called as a flotation principle. So it is called as Archimedes principle as well. So I am utilizing flotation principle. So as per flotation principle, what I have, so as per flotation principle I am assuming that there is a boat. It is called as a area of boat, naming it as a and it has been placed into the water and I am finding it out it's a density as well. So density and its density I'm mentioning as a d1. So I'm just utilizing that volume of it. So you can say that density d1 is equals to mass upon volume. So what I'm utilizing is a m is equals to d1 into volume. So I am utilizing all those data, naming it as either you can just give it that a volume equals to mass upon, it is also possible, volume equals to mass upon d1. So the same thing I am utilizing, and my density is called as a d1. So I can have V of a boat is equals to area multiplied by d1. This is the very first calculation I have just placed. Now, if elephant is placed in the boat and then density would be d2, then there is some displacement in the water. So by same equation, V of elephant is equals to area and displacement or density would be something different. Let's say this is first one, this is second one. I can say that the difference V dash is equals to V of elephant minus V of boat. I can have AD2, AD1. So by putting their densities, I can be in the position that this much amount of volume is been displaced, and then volume is displaced. I can find it out my mass as well, because I have this formula. It is called as density available to us, volume we have, then we can just place that m as well. So this is the very primitive question where we can place our normal general questions or general knowledge with some of the mathematical data, and we can find it out our all those questions answer. Now the third question in front of me is called as a wind speed during the storm. So you can find it out during the speed uh, during the wind. Let's say I want to find it out speed of storm. What I will do is that, let's say I'm standing over here and I'm putting a balloon over here. Let's say this is balloon's position, this is called as a height, and after some point, with the help of velocity of a storm, it will reach to this position, and this is called as a L, this is called as a theta. So you can just say that AB equals to height of balloon and BC is called as it's a displacement. So what you will do with the help of this, so you can have angle is equals to arc by radius, or I can use that parallax method. So in the parallax method, there is no type of a specification. They have mentioned that there must be a circular, or you can say that area would be spherical. There is no such type of specification. So you cannot say that every time you need a circular geometry. But here you can use the concept where I have utilized those data which are not circular in any type of manner. So you can directly utilize all those data in front of you and find it out what will be available to you. So there is no need where you can just say that, okay, I need such type of data or specific type of thing, or you can just say that Pythagoras can be applied. So you can find it out L as well. It is called as a distance or displacement. If distance or displacement has been found it out, speed equals to distance divided by time. You are knowing that previously your object was at position number B, and after interval of time it is reaching at position number C. So now you are very much accurate about the distance upon time. Distance can be measured with the help of parallax method. Angle equals to arc upon radius. So this is the thing where you can just say that theta is equals to what. So this is the example number third one. Now fourth one, we have to find it out a number of threads, means on your head how many number of hair, number of threads of hair you have to find it out on your head. So this is another good question. Previously you haven't thought about such type of questions, but right now they are just forcing you, ticking your brain how to find it out. For that I am using one simple formula. Number of a strand of hair is equals to area of a head divided by area of hair. You can utilize two things and you can find it out all those calculations. So first of all, I'm utilizing one small data I have available to me. It is called as a diameter of a human hair, and that is called as a standard value 10 to the power minus 3 meters. We are aware that area, for the area I require pi r square, so I can just see that pi d square divided by 4. So very first thing I'm just finding it out is that area of my hair. Now you will be asking question that how we can find it out, or how we can say that diameter of human hair is 5 cross 10 to the power minus 3. With the help of a micrometer in a practical you will learn how to find it out diameter of a human hair, and that is the proved calculation. 3.14 cross 10 to the power minus 3 cross 5, it's a square, and divide by 4 we have. So my area I am putting it as it is called as a is equals to 3.14, 5 square is a 25, 10 to the power minus 6 divided by 4 meter square. It is called as a area of hair, and I am naming it as equation number first one. The main formula is called as expression number A. Now I want to find it out area of head. To find it out area of hair, normal radius of a human head is a standard value. It is called as 8 centimeters. So I can have another area. It is called as a pi r square. So A is equals to 3.14 centimeters square means 8 square. So I can have A is equals to 3.14 multiply by 64 centimeters square. So now I have all those data available to me. This is equation number second, and that is called as a area of head. You can see from the data that I have used this formula. Number of a stud of a hair is area of head and area of hair. I have this much area of hair and this much area of head available to me. So all those data available to me. Now I am putting all those data as value in my expression. So I am using this notation. Equation number 1 and 2 implies in equation number A, means this one and this one is applied in expression number A. So now I am placing their values. So number of hair is called as n, and the value of number of area of head is a 3.14 cross 64, and this would be 3.14 25 10 to the power minus 6 and divide by 4. So this is the values I have placed over here. So n is equals to 4, 3.14, 64 divided by 3.14, 25, 10 to the power minus 6. So I can have n is equals to 3.3 gone, 4 and 64 and 25, 10 to the power minus 6 is going in the numerator. So I can have a 10 cross 10 to the power 6. So number of hair is not properly equal, so I am just removing this sign, is approximately 10 to the power 7. This is the number of hair, standard value, hair threads on a human head. So you can just previously you may have asked us, or somewhere you may have asked such type of questions to your friends that number of hair on a human head is what. Whenever we are clueless about some number, we were using such type of data. We were using that to count it out your hair on your head. So this is the number 10 to the power 7 is the appropriate data available to you, and it will give you the value how or now we have question number fifth one. In this fifth one they have asked us that the number of air molecules in your classroom. So we have to now find it out air molecules. So our fifth number is called as air molecules in classroom. So now we have to find it out air molecules. So first of all, we are not sure that how many what will be the size of your classroom. So we are first of all only utilizing equation volume of classroom is equals to V is equals to LBH. So and you are aware about normalized temperature pressure. The volume of atoms is equals to 22.4 liter, and I have already told you 1 liter is equals to 10 to the power minus 3 meter cube, because in physics we are not dealing with the liter unit. So I can have my volume as a 22.4 cross 10 to the power minus 3 meter cube. This is my first volume. Next is called as the Avogadro number. And chemistry you will be aware about such type of number. So Na is called as a Avogadro number. It is called as a 6.023 cross 10 to the power 23. This will give you that proper amount of number, because whenever you are using that 1 gram of let's say salt and 1 gram of sugar does not contain the same number of atoms, at that time you are in need of Avogadro number. So I have this much formula: multiply by volume divide by standard value of NTP, that is called as a 22.4. so this would be 6.023 10 to the power 23. I am not putting LBH because I am not sure that what would be the length, area and breadth of your room or height, and that is why I am putting as it is. You can also calculate by for your room as well. So this would be 22.4 cross 10 to the power minus 3. It is your number. So with the help of this equation you can find it out number of molecules present in your rooms. So these are the data available to you. So such type of 5 different type of questions are there, and we have found it out what would be its calculation of total mass of a rain bearing cloud, mass of an elephant, wind speed during a storm, a number of strands of hair on our head, and the number of air molecules in your classroom. So with the help of science or scientific data, or with some little bit knowledge of your common sense, you can calculate all those things very properly. Now we have example number 2.23. In this one they have mentioned us that the sun is at some point where we have to calculate its data, where it is in the form of a plasma. It is called as ionized matter, with its inner core of a temperature is exceeding to 10 to the power 7 kelvins. At this point of a 6000 Kelvin high temperature, no substance remain will be in the solid or liquid position. So they have given us mass of the sun and the radius of the sun, and we have to just calculate whether is it possible that our data or our density will be in the form of a solid or liquid or gaseous format. So we have to just check it out. Mass of the sun I'm mentioning in the terms of ms, and the radius of a sun which is in this term of rs. So 2 cross 10 to the power 6 kilogram, and a radius is a 7 cross 10 to the power 8 meters. So you are aware about equation density it is called as a mass divided by volume. So you can have density represented by rho, mass of the sun is rs, and you are aware that earth, its shape is considered as a sphere, so its a volume is called as a 4 by 3 pi r cube. Instead of radius we will put that rs is cube, so we have a 4 by 3 pi rs is cube. So I can have a rho is equals to 3 by 4 mass of sun pi rs cube. Now I am putting all those values. 3 mass of sun 10 to the power 6 kilogram, and careful that it is not 6, it is 30, so it is called as a 10 to the power 30 kilogram, because very tiny weight would be there, and it is not clearly should look like a 6 would be there, so I have mentioned 6 but actually it is 10 to the power 30. And 4 3.14, radius is proper, 7 cross 10 to the power 8, and it's a cube. So I have calculated all those data. It is a 392 10 to the power 3, so I can just utilize and round it off. It is 1.4 cross 10 to the power 3 kilogram per meter cube. This is the density where no gaseous atom can exist. So you can say that it's only possible for solid and liquids. So it is not possible for gaseous atom. So they have asked us that by practical value you can, after interval of a time, learn that how this is possible, because right now you are not sure about that density of a gaseous element, density of a liquid element, but yes, by practical value, by gradual interval of a time, you will learn that how it is possible. Now example number 2.24 we have. When a planet Jupiter is at a distance of 824.7 million kilometers, so I am just mentioning that small d, it is called as distance of Jupiter. So it is given is called as a 824.7 million kilometer. So I'm mentioning that 824.7 million 10 to the power 6 and kilometers, that is why I'm putting that kilometer only. And its angular diameter is called as a 35.72 seconds. So mentioning that theta is called as angular diameter, it is 35.72 seconds. Now I want to convert in the terms of radians. So you are aware that how to convert in the terms of radian. So theta is equals to 35.72 multiplied by 4.85 10 to the power minus 6 radians. So I have both data available to me. Now I want to find it out. My capital D is called as a total diameter. So I can have my theta is equals to capital D by D. I want to find it out capital D theta into small d. So my capital D is equals to value of a theta and all those data I'm putting. So minus 6 and plus 6 can be cancelled out. So 35.72, 4.85 and 824.7 will give me 142873 kilometers. An ideal way to write it out in physics is called as a mentioning in the terms of 10 power. I can have a 1.4 cross 10 to the power 5 kilometers. So this is called as a distance, diameter of a Jupiter. So I have done decimal points, and this is the data which are available to you. So this is the end of your exercise examples, but yes, in next clip we will discuss about some of the extra examples. These examples are good for your better understanding how you have grasped your concept, and for practical applications it is called as a mixed or combination type of examples. So we will solve such type of examples in next clip. So revise all your theorems, do a practice of your examples, and apply it frequently, and then you can master it out on all your examples. This is the very primitive key to have a good grasp or hold over the examples. Hope you will like it, or you will just go through the some of the theorems concepts frequently, and you can grasp these concepts of examples very well. Thank you.